Well, in addition to factor change, discrete changes, we can also calculate partial or marginal change. So first, let's talk about partial change in predictive probability. In addition to factor change and discrete change, we can also talk about what is called partial change or marginal change. The main difference between partial change and discrete change is that, for discrete change, in xk, generic variable xk, there is a discrete change or perceptible observational change. Okay, but for partial change, we're also talking about ratio, that is the amount of change in, well, either the expected count or probability, okay, relative to infinitesimal amount of change in xk, the generic variable xk. So the change is infinitesimal, very, very small, and unobservable to human vision, right? Very, very small. And that's the reason why partial change and marginal change is also called instantaneous effect. Instantaneous effect. That is, the amount of change in xk, this generic variable, is so small that is we can almost say that's instantaneous, okay, change or effect. Okay, so partial change and marginal change are also measures of effects. That is, the amount of change in y, the response variable, some measure of the response variable, right? Relative to the amount of change in xk. But for partial and marginal, the amount of change in xk is infinitesimally small. Okay, that's the reason why sometimes we call them instantaneous effect. So in this case, let's begin with the partial change in expected rate. So for the Poisson regression model, the expected rate or expected count is equal to the expectation y given x, which is equal to the exponential function of x beta. And for different x vectors, we're going to have different expected count. And the partial using calculus turns out to be this number, mu multiplied by the coefficient for this generic variable xk. So when we're talking about the partial change, the instantaneous effect of xk expected rate, it's going to be product of mu, okay, that is exponential function of x beta multiplied by its corresponding coefficient beta k. Okay, the value, note that the value of marginal or partial change depends both on beta k and mu, right? The expected count. So when beta greater than 0, the larger the expected count, the larger the rate of change in the expected count. Since the expected count, expectation mu, depends on all variables, the marginal depends on the values of all variables too. Often the marginal effect / partial change is computed with all variables held at their means, but not necessarily. Next, let me talk about partial change in the predictive probability. Now the quantity in the numerator is different. Okay, that is the amount of change in y, the response, the unit of the response variable becomes what? Predictive probability, as opposed to expected count in our previous 2 slides. Okay, so the partial change in the predictive probability is what? Well, in the Poisson regression model, we know that the probability function is defined as this formula, right? And the partial, as we go through very tedious computation, turns out to be this quantity. That is the response of our interest. Okay, multiplied by mu, the expected count, raised to the power of y, minus mu raised to the power of y plus 1, divided by the exponential function of mu, that is expected count, multiplied by y factorial. Then the whole term here, the ratio here, multiplied by beta k, that is the coefficient for xk. In this case, mu, as we all know, is equal to the exponential function of x beta. Again, this describes the instantaneous effect of xk on the predicted probability. In this case, we can say the instantaneous effect of xk on the predicted probability, as opposed to in our previous slide. Okay, here we're describing the instantaneous effect of xk on what? On the expected count. Okay, so two different quantities of the response variable. Okay,